Hello everyone! Welcome to this interactive binary tree visualization demo. Today, I'll walk you through how this tool brings a binary search tree to life. You'll see how it handles traversals, finds the lowest common ancestor, calculates the diameter, validates the tree, and even animates code for insertion. All with a cool visual twist. Let's get started. 1. Overview of the interface. Let's start with the layout. Tree visualization. At the top, you'll see a tree made of circles, that is, nodes connected by lines. Each node has a value, with left and right children branching out. Control panel. Below that, there's a set of buttons for operations like traversals, finding the LCA, calculating the diameter, validating the BST, and animating insertion. Output section. This logs the steps and results of whatever operation you run. Step 2. What's a binary search tree? Before we dive into the features, let's understand the tree itself. This is a binary search tree, BST, where each node has up to 2 children, a left child and a right child. Left subtree values are smaller than the node's value. Right subtree values are larger than the node's value. Our demo starts with values like 50, 30, 70, 20, 40, 60, 80, 10, 25, 90. Notice how 30 is left of 50, since 30 less than 50, and 70 is right, since 70 greater than 50. This structure is key to how BSTs work efficiently. Step 3. Exploring traversals. First are the traversal buttons. These show different ways to visit every node in the tree. Level order goes level by level, left to right. For our tree, 50, 30, 70, 20, 40, 60, 80, 10, 25, 90. In order: left subtree, root. Right subtree. In a BST, this gives sorted order. 10, 20, 25, 30, 40, 50, 60, 70, 80, 90. Pre-order. Root first, then left, then right. Great for copying a tree. Post-order. Left, right, then root. Useful for deleting a tree. Click a traversal button and watch the nodes light up in sequence while the output logs each step. It's a fun way to see how the tree gets explored. Finding the lowest common ancestor, LCA. Next up is the lowest common ancestor, or LCA, feature. The LCA is the deepest node in the tree that has 2 given nodes as descendants. It's like the closest shared grandparent between them. In a binary search tree, finding the LCA is super efficient because of the BST property. Left children are smaller, right children are larger. Let me break it down and show you some scenarios you can try in the demo. How it works. Start at the root, 50 in our tree. Compare the 2 values you're looking for with the current node. If both values are less than the node, move to the left subtree. If both values are greater, move to the right subtree. If one value is less and the other is greater or equal. You found the LCA. It's the current node, because the paths to the two values split here. Scenario 1. Nodes in the same subtree. Let's try finding the LCA of 20 and 40. Start at 50. 20 and 40 are both less than 50, so go left to 30. At 30, 20 is less and 40 is greater, so 30 is the LCA. It's the deepest node where 20 and 40 diverge. In the demo, enter 20 and 40. Click LCA, and you'll see 30 highlighted with the output saying, LCA is 30. Scenario 2. Nodes in opposite subtrees. Now, let's find the LCA of 40 and 60. Start at 50. 40 is less than 50, but 60 is greater. The paths split at 50, so 50 is the LCA. Try it. Input 40 and 60. Click LCA, and 50 lights up with LCA is 50 in the logs. Scenario 3. One node is the LCA. What about 30 and 20? Start at 50. Both 30 and 20 are less than 50, so go left to 30. At 30, 30 matches one of the values, itself, and 20 is less. Since 30 is an ancestor of 20, 30 is. Edge case. Node not found. If you enter a value not in the tree, like 15 and 18, the algorithm still runs, but might not find a proper LCA if one value doesn't exist. In our demo, it'll say LCA not found if the logic can't resolve both nodes. This feature is awesome for understanding tree relationships. Play with different pairs to see how the LCA shifts. Validating the BST. We need to make sure this is a proper BST. The Validate BST button checks, is every left child smaller than its parent? Is every right child larger? If all's good, you'll get a success message. If something's off, it'll highlight the problem node and explain why. Our demo tree is built correctly, so it should pass every time. Why this is awesome. Binary search trees are super useful. They make searching, inserting, and deleting data fast. Think databases, file systems, or even autocomplete features. This demo lets you see how it all works, making those abstract ideas concrete and fun. And that's it. You've now explored this binary tree visualization demo, from traversals and LCA to diameter, validation, and code animation. Play around with the controls, tweak the values, and watch the magic happen. I hope this makes BSTs clearer and more exciting for you. Thanks for joining me, and enjoy experimenting. If you like this video, then you will like the video showing on the screen now. So click on that. We'll see you there. Bye.